21.6, pause, okay, esters. An ester functional group, as you know, is less reactive now than the previous couple of functional groups that we've been dealing with, and we're going to see that the chemistry becomes more limited with them. A famous example of an ester, one that when I was an undergrad we made in laboratory, is aspirin, or acetyl salicylic acid. This is the chemical structure of the NSAID, non-steroidal anti-inflammatory drug, aspirin. Of course, now there are many modern variants of that, like ibuprofen or Advil and naproxen. The mechanism of substitution of these is very similar. I'm going to start here with a simple reduction. This time we'll bring in the aluminohydride. Now, unlike the other reactions, when we make the carbon-hydrogen bond, that is effectively an irreversible reaction for our purposes. That strong carbon-hydrogen bond drives this reaction. And we're left with alane, the aluminum hydride. It would be complexed to the oxygen, but I don't want to muddy the waters for us here. This then will kick out the oxide, and in fact it's going to get picked up by the aluminum. And this is again effectively an irreversible reaction, not because we can't add back to the carbonyl, but because we make an aluminum oxygen bond that's just much stronger. And so this then gives us another aluminohydride that's negatively charged. Then the second equivalent adds, we create another tetrahedral intermediate. And this alkoxide then is protonated on workup. All right, so that's the fundamentals of the mechanism. Make sure you can push the arrows and you know the difference between a carbon nucleophile or a hydride nucleophile adding, which is irreversible, and other nucleophiles that are reversible in their addition. Okay, so now let's look at the chemistry of an ester. Now I've kept this sort of explosion chart because I want you to see the realm of reactions is decreasing. As we go to more stable functional groups, there are fewer reactions. So we just saw the reduction. In the case of the ester, there's no longer two equivalents of this ethanol in this case. That was left up there from the anhydride. But we can reduce that with lithium aluminum hydride. It goes all the way down. We don't add Grignards. Well, you take that back. Grignards do add to this one. And in fact, they add twice. And make the tertiary alcohol. We've covered that before. Cuprates don't add to esters. We can hydrolyze them, but we need an acid catalyst. Now, we didn't need the acid catalyst for most of the acyl chlorides or even the anhydrides. They'll readily react with water, pushing the equilibrium to the carboxylic acids. We don't convert these to anhydrides, and interconversion of esters is not very useful because you're going to get a nasty, messy equilibrium. So make sure you practice those and understand now the limitations as we go to the new and more stable functional groups that are therefore less reactive.